Hello. The question here is, can we excavate easily or are there cables underground? Well, the answer is given by ground penetrating radar, which is another variety of microwave-based non-destructive testing. Let's look somewhat closer to that. The ground penetrating radar, for short GPR, is used in many applications such as archaeology, civil engineering, forensics, geology, and utilities detection. And it is then used for the detection of pipes, rebars, and so on, underground and in walls. The main principle is a radio echo sounding. That is, a short electromagnetic pulse is injected into the ground and then the echoes are received. These electromagnetic echoes are influenced by the properties of the ground. That means especially the permittivity epsilon r and the conductivity sigma. And the results are then displayed in a special way. That means the horizontal position in a horizontal line and the two-way travel time of the pulse downwards. We will see and look to that in the following. But before doing this, let's look to the properties of the typical ground material. We will only look to a few of these values which are given here. Let's look to the columns 1, 2, 3, that is material, permittivity, and the conductivity. Air has a relative permittivity of 1 and is not conducting, that is, conductivity is 0. Distilled water at GPR frequencies has an epsilon r of 80 and low conductivity. Dry sand has a permittivity of 3 to 5 and also low conductivity. While clays have a certain content of water, and so they vary depending on the water content in the permittivity from 5 to 40, and especially the range of conductivity is very high, from 2 to 1000. Well, the water conductivity depends on the amount of salt in it. For example, we see here the seawater with a conductivity of 3000 compared to distilled water with 0.01. And the water content of the material strongly influences its conductivity, as we have seen in the case of clay. This conductivity leads to attenuation of the electromagnetic pulse and therefore also limits the penetration depth of the electromagnetic wave. And that means also the observation depth for defects and some reflectors. The penetration depth, that should we know, is high as low microwave frequencies. So to check what the best microwave frequencies would be for GPR, let's look to the whole microwave spectrum. You know, it extends from 300 megahertz to 300 gigahertz, and respectively the wavelengths are 1 meter to 1 millimeter. And the typical services are the audio radio, the mobile radio, the microwave oven in the kitchen. It is the Wi-Fi, that are distance radars for ships and aircrafts. That is the direct satellite TV with the dishes on the houses. That is the professional satellite communication. It is the distance warning radar for cars, and it is the personal scanner at airports, for example. The low frequency region is the region from 300 megahertz to up to 2 gigahertz or even 5 gigahertz, the region which is used for ground penetrating radar. And that is a good compromise in the sense that a higher frequency would lead to a better spatial resolution. But the penetration depth in that case would be so small that would make no sense. So this is the typical frequency region for GPR. So let's look to the functional principle of the ground penetrating radar. We have the transmit and receive and antenna module, which altogether by the GPR people is called the antenna. This irradiates a short electromagnetic pulse into the ground. The pulse shape is sketched here. It is a small section of a sinusoidal oscillation. A part of this radiated pulse hits a reflector and then is returned to the antenna and received by the receiver. Then the time between the transmit and the receiving of the pulse is measured, and that is called the two-way travel time. And this time varies when the antenna is moved under the ground. Let's look to an animation. Here on the left-hand side, we have the position of the antenna and the reflector. And here on the right-hand side, we have the horizontal position, and downwards we have plotted the two-way travel time. So here it is larger than it is here. Now we let the position of the antenna move horizontally, and the two-way travel time is plotted. It decreases, and here it is minimum because the distance is minimum between the antenna and the reflector when it is just above it. Then the two-way travel time increases again. The curve which emerges here is a so-called hyperbola. We see it here in principle, and in practice we see it here, measured with a GPR instrument. Here we see also a horizontal line. This can be caused by a surface between two different ground materials. Let's look here. The radiation hits a boundary between two layers with different permittivity. And as we know, then reflection occurs. The amount of reflection is larger, the larger the difference in the two permittivities is. And this reflection holds on when the antenna is moved over the ground, which results in the horizontal line in the diagram. Let's look at two examples. Here, the position of an underground storage tank below a lawn is searched. The test shows a combination of hyperbolas here and horizontal lines, which result from lumped or elongated reflectors and different ground layers. The second example shows a GPR in another area where various service structures are underground. Water pipes, electrical cables, gas pipes, and a sewer system. The test drawing shows many indications and need careful further evaluation. In future application videos of this channel, we will see several GPR applications in more detail. So far for today, we have learned how ground-penetrating radar works and in which situations it can be used. So, thank you for watching. See you next time. Goodbye.